Okay. Good afternoon, everyone. So I hope you had a great session during your exam. A good kind of a experience you had while giving the exam. And today or these 3 days, we will be covering with some of the left out topics, except the quantum cryptography as well. So we will be, thank you, Varsha. So we will be covering some of the quantum error correction. We'll start it. And then we will also start a few parts of the classical cryptography or some of the concepts of that. Okay. So today, primarily, we will be considering or looking into one of the quantum error correction code, and we'll see some sort of improvement with respect to another code. But these codes, again, just like the quantum algorithms, these are very primitive error correction codes, but these are fundamental or kind of like a, say, foundations of QECC, quantum error correcting code. Okay. And before I start it, also just to keep some of the points in mind that why we need error correction and how it can improve our performance, we will be also discussing some of the things. I haven't prepared much of the slides today because I thought of explaining it with the like a whiteboard only. So a very few slides I have prepared. And once we will be doing all the error correcting codes and all, so just try to make your own notes while I'll be doing the like session. Just try to also write it down somewhere. Okay. So on that note, we will start. So fundamental relation between the errors in classical communication and in quantum communication. This is the first topic that we will be discussing. So what is the error? In a very easy word, what is the error? Okay. So error means if there is any deviation with respect to what I should get and what I am actually in real time getting. The difference, that is an error. And our inability to actually access or kind of a control that situation to take place is known as a failure. Okay. And that particular, say, the deviation is known as a fault. So this is the relation between fault, error, and failure, right? So error means I should be getting somewhere, maybe I am sending a bit stream, okay, of zeros and ones. So if at some place I am getting a 1 where I should be ideally getting a 0, that is an error. Or if I am getting a 0, but ideally I am getting a 1, then also we will call it a error. That is wherever there is a deviation with respect to the intended output and the actual output. Okay. So during transition of data, signal might get corrupted. And why this error happens? Definitely because of certain corruption in the signal that is being sent from sender to receiver. So leading to receiver receiving some data different from what sender had sent. So the integrity or data integrity will deviate. Okay. So, and also requirement of error detection in order to correct errors. That is a kind of a requirement that I have in classical communication as well as in any communication. Of course, we want some valid transaction to take place in terms of what? Even a data transit. Okay. So when we call it a single bit error, if say for example I am sending 8-bit data stream, if there exists error in only 1 bit, we call it a single bit error. Okay, and there is a different probability of finding that single bit error out of the all 8-bit errors. If I can get error in multiple positions, we can also call it a multiple bit error. And often some kind of like consecutive bits together, we call it as an error. So yes, that is what I'm telling. So often we might actually search for a certain kind of a phrase where at these positions, maybe I should be getting a 1-1 where, but I'm getting a 0-1. So altogether, that also might determine a single bit error or a single unit error. That can also happen. That depends on our set of requirements, what we have. Okay. So often we might see actually for the error correction purposes, okay, we might check that what is the like value at position, say for example 0, 1, 2, 3, 4, so fourth and fifth pin together. So if I get a substring of 0, 1, then I should call it okay. If I should be getting only 0, 0, and I'm getting any other symbol, then I should be calling it an error. So that can also happen. So it's a single bit, but here a bit refers to unit of information. Okay. Let's discuss the questions on 12th. I guess we're already done with the exam. So few questions I got. I get to know that you have certain doubts maybe with the options and all. So let's discuss everything in the on 12th. But if there is a case where in question number itself there is certain error, we will definitely look into that. Okay, or in options maybe. Okay. So if now depending on our communication protocol, we may ask for, I will call it as non-erroneous if I exist an even number of ones in the bit stream. So that means I will make a XOR of all the ones that I'm getting, and if I'm getting a 0, I will call it okay if I'm not getting a 1, or if I'm not getting a 0, I will call it an unacceptable. That is where I'm getting an odd number of zeros instead of an even number of zeros. So this is how we set a communication protocol, that it should work on even number of ones. Sanjay, is the screen visible to others except Sanjay? Screen is not visible. Slight disturbance, visible. It should be visible. From my end, there is no error. Okay, thank you. Thank you. So please try to rejoin. Please try to rejoin for those it is having certain or showing certain error or you are unable to see the screen. Okay. Yes, I'm trying to be a bit louder. I have certain issue with the voice. I have certain issue with the voice, but it shouldn't be like breaking due to the network error or something. So if there is an even number of ones as per the communication protocol, we call it a valid one if my system or the function that will approve it to be a valid communication approves the even number ones to be sent. If it is otherwise, then we will call it an unacceptable one. And for all these errors, what we do is the way parity checking is one of the way. There is another way which is called the redundancy bit addition. So what we do is if we have to send a 0, so we represent it in form of a 0L, which is a logical 0, 0 logical, and we put some redundant bits. So for 0, we will be putting 0, 0, 0, and for 1, we will be putting 1, 1, 1. Now, say in output, we are getting a 0, 0, 0. Then, of course, it represents a logical 0. But if it is a 0, 0, 1, that will also represent a logical 0, 1, a logical 0. Why? Because we will assume that maybe out of the 3 bits, the probability that 2 of the bits got distorted is much less than the probability that only 1 bit has got certain distortion and it has become 1. So 0, 0, 0 can become 0, 0, 1 or 0, 1, 0 or 1, 0, 0 is more probable than occurrence of 0, 1, 1 or 1, 0, 1 or 1, 1, 0 or altogether 1, 1, 1. That is all the error in all 3 bits. Because of the probabilistic outcome, we call it a majority voting, where the maximum number of zeros will represent that it is a logical 0 and maximum number of ones will represent a logical, just because of the probability. Because the chances of error and chances of not having the error are often not equal. Okay. And even if it is equal, it is like say 0.33. So it's 0.33 times 0.33. So in that way, it will be actually even less than that. Okay. So it's 1/3 of 0.33. So it's even less than 1/3. Okay. So in that way, we actually use the concept of redundancy, which is a way of detecting errors and auto-correcting them, where data is constantly monitored and corrected by the principle of majority voting. Okay. So errors in quantum communication. Now, this is a basic thing that we all have seen and we all have known, even with a very detailed way. We have seen cyclic redundancy checking, where we actually perform division of 2 kind of polynomial. We add accordingly some number of redundant bits, and whatever we got as a checksum, that is the kind of place which we again use for error correction. So in that way, we know a bit of like error correcting, error detecting, and error correcting codes in classical. So you all know about it. But the thing is that for errors in quantum communication, there are a few things that you should be considering. What is the first thing? That is, if we want to send multiple logical qubits in place of actual qubits, qubit states needs to be duplicate. Why? Because of the redundancy to take place. Okay, but quantum no cloning theorem prevents the same. You cannot really replicate an existing quantum state unless and until you know exactly the conditions on which those like that qubit or those particular quantum states are built on. So you do not have that idea. So that means your quantum no cloning theorem will work there and you will be unable to clone a particular system or a set of particular systems. Okay, which is very kind of a primary logic for redundancy. The second one is, unlike your classical communication, errors in quantum states cannot be measured directly, as states can be either in a pure state form or it is in a linear superposition of multiple states. I just want to give a pause here. Are you all able to see my screen and clearly see my, clearly I'm audible to everyone? Can hear my voice?
I am able to see the PPT and hear your voice. Maybe you can also once again maybe reshare again, uh, exit share and reshare once again.
Okay. I think it is too like some is okay and some is not okay.
Yeah. Here,
So
in the center, we are able to see WebEx where you are sharing. We are able to see the very clearly the now it is showing errors in quantum communication with a into
yes,
X mark. Yes.
yes. Let me continue a bit. If I see some kind of like comments, and I will again try to rejoin. I hope that is okay.
Yeah. Okay.
But we started with these things. This was the first slide, errors in classical communication, followed by this thing, where the redundancy and parity is being discussed, followed by the errors in quantum communication. So currently we are in this. Thank you, Satya. Thank you. So, unlike classical communication, errors in quantum states cannot be measured directly, as states can be either in the pure state or it is in the superposed state. So that means the measurement postulates will come into picture whenever it is a linear superposition of quantum states or multiple states. And that also means because of the uncertainty in measurement outcome, I might not often be able to perfectly predict that what output I am going to get. So unlike classical communication, errors cannot be that easily detectable in case of a quantum communication. Okay, because of the measurement postulates and measurement uncertainty. Though I am doing after the quantum stuff is done, I might do it in classical way, the measurement, but it need not give me always the desired outcome. Rather, it can be outcome can be random. So there is an uncertainty there. So that is another challenge that we have in quantum communication, and measurement would collapse or would cause certain collapsing of quantum state into one of the basis states. That is the issue itself, because it can collapse into any one of the basis states, need not to be like in the desired one that I should be getting. Okay. So error now is the thing that error due to decoherence in quantum communication. First is, now why this kind of error thing happens, really happens. For quantum, with respect to quantum, now for classical we know that often certain maybe there is a error in the channel itself, or some of the bits might got distorted. So that is kind of error that can happen, or cause error that can happen in classical communication. But with respect to quantum communication, the result is not always that much of simple. Why? Because often the channel error might not be the real cause of error here, or the distorted bit. Why? Because here it is itself the quantum channel that is taking the quantum bits through it. And that is very much in a nanoscopic level. So at a microscopic level, some sort of distortion to take place is a very challenging one, unless and until there is a very targeted attack. So one kind of attack can take place which can directly affect it with respect to the hardware level, that is a side channel attack. With respect to the hardware components that might cause certain error. Otherwise, there is a very less chance of some error that can happen because of some external agent. But internally itself, quantum communication is fragile. Why it is very fragile? Because of the fragile nature of the quantum states, as they are very likely to decohere by some interaction with respect to the surroundings. And maintaining a coherent superposition of multi-qubit quantum states over a period long enough to complete a quantum algorithm seems a very difficult task. Okay, VCB Rao, I guess it is visible to others. Let me take some other comments, then I guess I'll be rejoining. Or should I be rejoining now? Uh,
Yeah, here it
it's
is.
visible.
Decoherence is visible. So maybe once you also try, ma'am. I think that will be sufficient.
Yes, because I think it's like 50 times I'm
Yeah,
getting
yeah.
it.
Half
Okay.
of them are able to see, and other half.
Half of them are able to see. Okay. Let me stop it and share it again. Or let me just leave the webinar once and then again join.
Okay, ma'am. Sure. Yeah, maybe you can look at YouTube also. Always we can check, because you can keep the YouTube video on and then let the audio be there. That's also another option. Anyway, let's see what's the issue. Yeah, let me check if it's a mobile problem. I'll also move to the mobile. I'll log in.
Now am I audible now? Again rejoined.
Yes, ma'am. You're audible.
Okay, let me share. Yes. Just yes. So I was discussing the second point, which is maintaining a coherent superposition of multi-qubit quantum states. So let me break it down. So multi-qubit means a multiple qubit, number of qubits. So that means at least, say for consideration, say 3 or 4 or 5 number of qubits. So that means at least 8 or 16, or say kind of for like 5 qubits with 32 number of states. So if all the 32, now consider n equals to 5. So all the 32 states, when they will be in a superposition, that means it will be a superposed quantum state of, okay, so superposed state of 1 by root over 32, that is the in a uniform superposition state, that is the probabilistic amplitude times within bracket ket 00000 plus ket 00001, likewise still ket 11111. Ket notation close and bracket close. Now all the 32 states, this entire state is in a, yes sir.
Ma'am, not visible. Slides are not visible. I think half of them it's visible again, I think. Yeah, actually in YouTube also we are checking. YouTube, it's not showing, ma'am, slides.
Uh,
Can you share?
is it visible to you, sir?
Now it's visible, yeah.
Okay.
Now it's visible.
Okay.
Please, no. Now, actually, what is visible is error due to decoherence in quantum communication. Yeah. Some people are saying,
Yes.
some people are saying no.
I think everyone, I can wait for 1 minute. Everyone, please try to rejoin again. For those who are having an issue.
Yeah, it is visible
Should
here.
be an issue. Yes, I'm just waiting for 1 minute, giving all of you 1 minute of time. Please try to rejoin in the webinar. Yes, I'm waiting.
Or others can move to those who are not able to. Yeah, one option is please leave and rejoin. Let's hope things get solved. Otherwise, please open YouTube link also. I'll share it on the group as well. So there it is already ready. So you can try to look at. वहाँ पे share कर दो.
Okay. Thank you, Shivashini. Thank you. Everything is okay from mobile. Okay. You can connect from mobile as well in that case. Okay, visible and audible. Okay. Okay, let me start again. So what I was telling is, if it is for a 5-qubit state, that means maintaining a coherence. Coherence is nothing but the amount of time that the coherence time or the feature coherence states, that amount of time or duration I should be able to hold the quantum information that I currently have. What's a particular information that I am supposed to hold? That is kind of a coherence. And whenever that starts like some diminishing, or that starts to kind of vanish, we call it a decoherence. So maintaining a coherent superposition, that is, I have to maintain the superposed state, and that has to be in coherence of all the 32 states over a period long enough to complete an entire quantum algorithm. For example, say Grover, which is a complex algorithm with respect to a lot of quantum gates and all circuit, everything. That seems a difficult task. So now we are creating the base that why we need a quantum error correction. The first point is the fragile nature of the quantum state because of decoherence that happens due to the environmental noise. The second one is to maintain the coherence. That is another challenge where we should be taking care of error detection and correction with respect to quantum. Okay, at least some of the supervision we might need there. Third point is the decoherence itself that would destroy the phase relation between states and the superposition. Phase relation means how much is the deviation between two states with respect to the Hilbert space or block here. That is another thing where because of decoherence, some sort of quantum error can take place. Okay, so decoherence is in what terms? In open terms, it is basically breaking the kind of a flavor of quantum superposition and quantum computing. Okay. Okay. Now, yes. So now I will be starting with some of the quantum error correction codes. I will be starting with that. So, is it working? Let me just see it. Yes. So we will start with the very first quantum error correction code. Okay. So there will be a condition that will be like kind of a fix to the system, that is the sender and a receiver, say Alice and Bo. They will be send a bit of data or some amount of information. Now, in quantum setup, we have to determine that whether the quantum state is distorted or not. So first of all, it should be an error detection. And if possible, then we will check that whether there is of error correction with respect to that detected error or not. That is our agenda that we have. So say for example, let me start. Say for example, let me do it with okay. Let me change the color for the next one. Say for example, Alice. I'm not sharing content right now. I'm just showing the whiteboard. I'm doing calculation there itself. I would request all of you to write it down if you are able to see the screen or able to follow from YouTube. Yes. So Alice is the sender basically, and sender Want to say something? Uh, uh, why that is happening? Should not be. Only PPT visible. Yes, in PPT itself, I'm using like whiteboard. Oof. Now whiteboard is visible. Thank you. Okay, someone is no, it's not visible. Still, I guess it will be recorded, so you should be able to see that visible. Thank you. Thank you so much. So psi is a quant because for some of the persons it is visible. So even if I try, I don't think there will be a, like solution for those who cannot see it. Now, okay. Thank you. Thank you.
Yeah, I think
Suraj.
some
So
of us,
this is
some of us can move to YouTube, please, because YouTube now I am able to see. Earlier there was an issue, but now it's okay. So either it will come here after some time, or please follow on YouTube. Thank you.
yes. From my side, I don't see any kind of a network issue or anything. So please just wait for some time. I guess you will be able to see it. So this is the thing. Okay. So where these two qubits are called ancilla qubits. For ancilla means you can as of now think it of a temporary qubits, where some of the results for error correction and detection you are using it. So some kind of temporary qubits are called ancilla qubits in easy words. And these two are synodic. So this is your 1, 2, 3. Okay, qubit number 1, 2, 3, where 2 and 3 are basic zeros. So 2 and 3, qubit 2 and 3, these are pure states, and qubit 1 is basically your ket psi, which is alpha ket 0 plus beta ket 1. Qubit 0 and qubit 3 is nothing but also ket 0. And these two are ancilla qubits. Okay. Now I am applying, say, what will happen after, say, this time instance? Say, let me call it T1, T2, say T3. Okay. So at T1, it is half 0 plus beta 1 times tensor product 0, 0. So it's half 0, 0, 0 plus beta 1, 0, 0, right? This is T1. Now let me apply the first C naught, which is the first step between how many number of qubits, like 1 and 2. So this is first and 2, 1 and 2. So I'll be applying a C naught or control naught. So it will be what? 0, 0, 0 plus beta 1, 1, 0. Okay. So this is after the first qubit or first C naught, where qubit 1 is control and qubit 2 is target. Then it is the second C naught, which is C naught of 2, 3. So now this is the second qubit and this is the third qubit, and here it is the second, here is the third one. So it will be alpha, just give me a minute, 0, 0, 0 plus beta, say, yes, so it was the 1, 0, 0, sorry, after, yes, it was 1, 1, 0, sorry. Now it will be 2 and 3. So it will be this thing, let alpha beta 1, 1, 1. So that will be my final step that I will be having at t equals to 3. Okay. And let me call it as psi 2. Okay. Okay. For some, I guess it is a big error. Let me pause here a bit. Let me pause here a bit. Let me again try and connecting. Again try and connecting. Just give me a minute. Let me again try and connect it. now again try to share my screen. Please let me know if it's now okay. Just a minute. Is it okay now?
Yeah. Slide is
My
visible.
voice and the screen? Okay. Okay. Thank you. Thank you. Thank you. Yes. Okay. So again, just to give you a quick recap for those who missed it. So what I have done is basically what I've done is I started with this is a basic quantum circuit. I got your confirmation. Focus on the slide now. So Alice wants to send the psi state to the channel to Bob. So Bob is under receiver end, and psi is arbitrary quantum state which has a certain kind of a configuration of alpha 0 plus beta 1. Qubit 0, qubit 2 and qubit 3 both contain the value 0, which are two ancilla qubits. Ancilla qubits are generally used to represent some sort of intermediate qubit or just to help in the computation. You can think it of just like the auxiliary qubits, it is used. So at T1, and these are two C0 gates. So at different time instances, so T1, T2, T3, what is the value or the status of the quantum states? Now we want to calculate that. So at T1, it is alpha ket 0 plus beta ket 1 times tensor product 0, this second qubit, product this third qubit 0. So this will be here, it will be alpha 000 plus beta 100. Okay, this is very simple thing. We have done a lot of such things, right? And this is the reason for which we have done all those things basically, just to understand the things very fast. So once I apply a first C naught gate, which is a C naught on 1 and 2, because this is 1, this is 2, this is 3, third qubit. So now C naught, this is the control, this is the target. So on 1 and 2, C naught 1 and 2, whenever it is applied, so this is 1 and 2. So it will make it 000 plus 110. I hope it is clear. Why? 1 is control, 0 is target, so 0 has been flipped or not. Okay. Now, second CNOT operation we also will be doing, which is a on 2 and 3. So this is your 2 and 3. This is your 2 and sorry, not here. So this is your 2 and 3, and this is your 2 and 3. So 0 will not have any change, but 1 will make now become 1 and 1. So alpha 0 plus beta 1 which is 2. This is your resultant state psi L or logical size that you can call it. Okay. Now, unable to see that thing. It's not coming for some reason or what, I don't know. Just a minute. Yes. So now for 3 qubit code, suppose the noise in the quantum circuit, please write it down. So you will be having a full understanding of these things then. Suppose the noise in the quantum circuit, say quantum circuit, flips a bit with probability P, say probability P, and leaves it unchanged, with a probability. Of course, it will be 1 minus P, no doubt about it. That is 1. It will be some error or flipping 1. It will be unchanged. And the state received and the state psi to L, which is received by Bob, is basically that thing. That is alpha 000 plus beta 111. Right? So now there can be a particular case. That is, say for example now, let me change the color. Say quantum states, a few calculations that we want to do. A quantum states received by Bob, either it is erroneous or it is not erroneous, we will be calculating it. Then followed by the probability. Okay. So initially it was alpha 0, 0, 0 plus beta 1, 1, 1. If Bob receives it, that means what? That is, there is no error. So it is not no error in first qubit times no error in second qubit times no error in third qubit. So it is basically 1 minus p whole qubit. Okay, because no error in first qubit, no error in second qubit, and no error in third qubit. Okay, so this is as it is. I'm just writing it in this way. Now say the second combination is whenever Bob receives something like that, say the first bit or first qubit, that can be erroneous, or the second qubit is erroneous, or the third qubit is erroneous. So it's all of the multiple possibilities, right? So it's either the first qubit, which is 0, 1, 0, 0 plus beta 0, 1, 1, or another case is, so this is 2, this is first case. Third case is, say, alpha 0, 1, 0 plus beta, this thing 1, 0, 1. So another one is alpha, this thing that is 0, sorry, that is, just a minute. Yes. So the third case is alpha 0, 0, 1 plus beta, sorry, it has now become this thing, beta 1, 1, 0. So if you check what is the similarity between all these three states, it has a similarity. What is the similarity? That exactly one position contains some error. And there are three possibilities that only one position will be having some error. So if I have to write it down, so for this case, it will be P into, that is in first position, there is an error, into 1 minus P, into 1 minus P, that is P into 1 minus P square. Or say this one is 1 minus P into 1 minus P, which is P into 1 minus P square. And this one is 1 minus P into 1 minus P into P, that is P into 1 minus P square. All these things together will make it what? 3P, that is plus. Okay, so 3P into 1 minus P square. Alternatively, we can also find it out in this way, that let me do here. So only one bit position will be having some error. So only one bit position out of 3 will be having some error. So that means the probability that there will be exactly one error out of the 3 possibility, where n equals to 3 will be the binomial distribution. That is, okay, so 3C1 into P to the power 1 into 1 minus P to the power 3 minus 1, which is 3 into P into 1 minus P square, which is 3P into 1 minus P square. Okay, that is the case. Now, similarly, the third one will be where there will be, okay, 1, 2, 3, 4 is done. Now, fourth, fifth, and sixth will be the cases where there will be exactly 2 errors. What was my initial state? Again, I'm writing here alpha 0, 0, 0 plus beta 1, 1, 1. Now, 2 bits position will be having some error. So, where it can be erroneous, like 1, 1, 0, we can start with that one. So, alpha 1, 1, 0 plus beta 0, 0, 1. Or it can be alpha 101 plus beta 010, or it can be alpha 011 plus beta 110. Okay. Now all these things, if you check, that clearly says a P of x equals to 2. Right. Now what that will be 3C2 into p square into 1 minus p to the power 3 minus 2, which is 3 again into p square into 1 minus p, that is 3p square into 1 minus p. That is that condition where it has exactly 2-bit error. Okay, and then the last one is this one. Okay, so the last condition. So I have here 1, 2, 3, 4. Sorry, it will be 7, but it will be basically 7, 6, and 5 because I covered 1, then 2, 3, 4, 5, 6, 7, and the last one is 8. So it will be the condition where all the bit position will be changed starting from this thing. So it's all 3-bit position will now be flipped. So it is 1, 1, 1 plus beta 0, 0, 0. So now the probability x equals to 3 is, any way you do it, so it's basically error in all positions. So p into p or CP cube, or you can also write it down in this way, say 3C3 into p to the power 3 into 1 minus p to the power 3 minus 3, which is 0. 3C3 is 1, so it is 1 into p cube into 1, which is p cube. Okay. Now all the probabilities we have find out. Got it? We are just doing the 3-qubit program. Now the quantum circuit is done here. Now we are analyzing based on what Bob can receive. That is what we are doing here. Okay. Now now once Bob actually has done all these things, these are the possibilities, the way Bob can receive. Now what Bob will do is, Bob will try to form its own error correction circuit. So now the kind of a quantum gate operation, sorry, quantum gate operation performed at Bob's end. So what are the all possible 8 states Bob can receive? We are now seeing, depending on different error and different positions. So his quantum circuit will be like this. So this is what phi to n that Bob has received. Phi to n is what Bob has received, so I'm just writing that. And again, I am introducing 2 ancillars. Okay. Now which will be 1, 2. Now see, it is 1, 2, 3, 4, and 5. So in 1 to 4, there will be a C naught. Then from 2 to 4, there will be a C naught. Then from 1 to 5, 1 to 5, there will be a C naught. And from 3 to 5, there will be another C naught. Let me write it down in some other color. So it is basically C naught 1 to 4. This is C naught 2 to 4. This one is C naught 1, 5, and this one is C naught 3, 5. Okay, and now in these 2 ancilla, I will be applying a measure gate, and whatever will happen then on these 3 things will actually made up to, there is a line, yes. So this will make up to the error correction based on the measurement outcome of this. So this is at what Bob will do at his receiver end. Okay. Now in the next page, we will look into all the possibilities and what will affect, or like what will happen on performing these two or like these four C0 gates on these two ancilla qubits. Considering right now I have 5 qubits. One is whatever we are referring, whatever we are getting from 5 to L, which comprises all the first 3 qubits, 1, 2, and 3, followed by 2 ancilla qubits, 4 and 5. Okay, and I'm applying the C0 on those two, considering those two ancillas as target, where my 1, 2, and 3 is what I'm getting at Bob's output. So just I'm putting those things as control and the ancilla as target, so that on measuring ancilla, I will be able to give, like, make a kind of a backtracking on where I got an error and what was that error and how I can correct it. So all these things will come based on whatever output I am getting on ancilla. And when ancilla will be affected, if I get anything which is not my desired ones. Okay. Now let me just do this is a 3-qubit error correcting code. I guess you are asking something else. You are asking probably what is the error content for a C0 gate for IBM. Is that what you are asking for? Like C0 error probability? That is a gate error that you are talking about. I guess you are asking the same thing. Yes. So that is a gate error or quantum gate error. So error can happen in different form and different ways. So this is the quantum information that I'm sending if there is an error in that, or the quantum state that I want to send if there is an error in that. But definitely my quantum gates, that can also be error based. Yeah. So erroneous quantum gate and erroneous quantum circuit will have an impact on the entire cost equations and all those things. But this is with respect to the quantum information. Why? Because we are slowly heading towards a quantum communication and cryptography. So this is just a prerequisite that how the error correction or while the two bits are actually in transit, so something on that can also be detected in between Alice and Bob. Okay, because the parity and redundancy, all those checkings are not really that much of a feasible thing here, because we cannot do the like no cloning. Okay, we cannot do the cloning, sorry. So because of that feature, we have to keep it in mind a certain constraints. Okay, so just let me give the illustration to you all. So say for example, phi to L is what Bob is received by Bob. This is your phi 3L. What is the final output that you are getting? Phi 3L is the final output on ancilla, on producted ancilla. Say, like let me write in this way. And this is the probability that you are getting. Okay. So first it is alpha Kate. Let me write down all the possibilities first. Alpha Kate 00, beta Kate 111. Okay. Then it is alpha Kate 100 plus beta 011. Alpha 010, 10. Those who are writing it can see it. Exactly, these are the all states that we have got earlier. So this is nothing new that I'm yet writing. Last one is okay. Now what will happen on ancilla? I will be writing it directly here. But remember, these are now these will be now I will be directly writing phi 3L on applying all the 4 C0 gate, all these 4 C0 operations. Okay, and what were the ancillars there? 0 and 0. So here everywhere it is 0, 0. Okay, likewise I'm just writing. Now write it down for you. Like you can skip it. It will always happen. Just for our calculation for class purpose. So this is 1, 2, 3. This is and this is 4, 5. This is 1, 2, 3. This is 4, 5. Okay. Now if you do apply all the 4 C naught, which was 1, 4, 2, 4, 1, 5, and 3, 5, you will see that nothing will happen for the first one. So it will be alpha ket 0, 0, 0 plus beta ket 1, 1, 1 times this thing ket 0, 0. And for this, it will be alpha ket 1, 0, 0 plus key beta ket 0, 1, 1 times this will now become 1 and 1. Just take it, it will be 1 and 1. Okay. And here, this is first, second, third, fourth, fifth. Once we are doing this, then we are doing 1, 2, 3, 4, 5. Now we will eventually see that 1, 1 will be coming out at the right hand side as a tensor, as a common. So it will be ket 1, 0, 0 plus beta 0, 1. This is what you should be receiving. So similarly, if I just write it down all the terms, it will be 0, 1, 0. These things will be as it is, but this will make your ancilla as 1, 0. And this will make your ancilla as, I guess, yes, so I guess it will make it a 1, 1 or 1, 0. Sorry, it will make it a 0, 1. And this one will make it, sorry. Yes, so it was 1, 1, 0. So it will make it 1, 1, 0 plus beta 0, 0, 1 times ket 0, 1. It will make it alpha 1, 0, 1 plus beta 0, 1, 0 times this will be 1, 0. This will be alpha 0, 1, 1 plus beta 1, 0, 0 times this thing that is 1, 1. And this will be your alpha 1, 1, 1 plus beta 0, 0, 0 times it will be your 0, 0. The probability will be 1 minus p whole cube, p into 1 minus p square. This is also p into 1 minus p square. This is also p into 1 minus p square. This is p square into 1 minus p from the same logic. P square into 1 minus p, p square into 1 minus p, and this one will be your p cube. So now that you have seen that what will happen in the ancilla. The ancillas have now become different. Okay. I can explain any one condition. In one condition, I can explain it to you. Let me take the second one. Let me take the second one and show that how this thing is coming. Okay, just one case. So it's alpha 1, 0, 0 plus beta 0, 1, 1. So that means it is, say, psi to L. Just a counter example. So psi to L was alpha 1, 0, 0 plus beta 0, 1, 1. And now I have added this 0, 0. Right? Now, there are 4 C naught gates. So 1, 4. Let me write it down all. C naught 2, 4. C naught of 1, 5. And C naught of 3 and 5. So after these, all these 4 C naught gates, let me write the respective states. So it is 1, 0, 0 followed by 1, 0 plus beta 0, 1, 1 times 0, 0. This is applied on 1 and 4. 1 and 4. Okay. Now 2 and 4. So it is 1, 0, 0, 1, 0. No change. Plus beta 0, 1, 1, 0, 0. And this one is alpha 1, 0, 0, 1, 1 now. Because on 1 and 5. Okay. So 1 on 5, 1 and 0. So it will make 1 and 1. Plus beta 1 and 5. So no change because 1 itself is this thing. So, okay, here I guess it was Yes, in this step it was 1, 0. It was on 2 and 4. So 2 and 4 will make it 1. So it was 1, 0. It was 1, 0. So now your 1, 0 will become on 1 and 5. 1 and 5, it will be as it is. No change. And then 3 and 5 means 3 and 5. So it will be 1, 1. Now you are getting it. So now it can be represented as final Q3L can be represented as alpha 100 plus beta 011 11. Okay. So whenever this is happening, that is 1 1, I'm not getting 0 0. I will identify what? I will identify that this, just wait a minute, there's a lag. This is a kind of a error detection. Okay. So this is a error detection at Bob said. So I have sent something, I have received something on some logic sent, as on some logic received. I've added to ancilla, done certain computation in order to detect it, just like we used to add in CRC some checksum bits. Here also we have added those redundancy bits. And after adding those redundancy or say ancilla bits, I have got something which is not initially initial ancilla status, which is 0 0. So now in this case, we have identified at least there is a some sort of error detection or error we can detect it. Okay. Now the thing is we have to correct this error. That is the next task. So error correction. Error correction in this 3-qubit QVCC is, once I have detected the error, now what I will be doing it. Now ancilla is measured. Definitely I will measure my ancilla. Ancilla is measured. And on measurement, we will getting what values? Say 0, 0, 0, 1, 1, 0, and 1, 1. Okay. Now say, the first case is say, ancilla is what? It is 0, 0. I'm just considering each of the status of ancilla that I can get in my output. Say, for example, ancilla is 0, 0. Now, if you check here, ancilla is 0, 0 for which condition? The first one, 0, 0, 0 plus beta 1, 1, 1, and on the last condition, 1, 1, 1 plus beta 0, 0. And also just see from the screen itself that for 0, 1 status of ancilla, I'll be getting exactly two output. That is 0, 0, 1 plus 1, 1, 0 and 1, 1, 0 plus 0, 0, 1. For 1, 0, I'll be getting these two things. 0, 1, 0 plus beta 0, 1, 0, 1 and 1, 0, 1 plus beta 0, 1, 0. Similarly for 1, 1. So for each of the obtained values of ancilla or status of ancilla, we can actually get two different or one pair of side 3L or two different side 3L values. So in that case, if ancilla is 0, 0, what I can get two results. The first result is alpha 0, 0, 0 plus beta 1, 1, 1. Or I can get alpha 1, 1, 1 plus beta 0, 0, 0. So this is correct state. Because why? Because this was the initial state that I wanted to send to Bob. But this is the incorrect state. Okay. Similarly, if ancilla is say 0, 1, ancilla is 0, 1, I'm getting two things. First is alpha 0, 0, 1 plus beta 1, 1, 0 and just the reverse. That is alpha 1, 1, 0 plus beta 0, 0, 1. So in both the things, you can see that it is basically the probability that you are having error in one term, this thing. Right? So this one is nothing but, sorry. Okay. Just stop it. Just a bit. Let me just create a few ones. I'm again showing it. Uh, Screen is not visible. No? Just stop sharing like this. Yes, we can share it. Just a minute. So whenever answer is 0, 1, this thing means I have error in only one term, that is px equals to 1, which is nothing but this thing, because I have only one combination. Okay. And I do not have the possibility to get 0, 1, 0. That is why I'm not taking 3, 3, 1. Okay. And this is a very specific case. That is why I'm just taking px equals to 1 and 3. The coefficient 3 is not coming into picture because I'm not choosing one out of the 3. It's a one of the specific combination that I'm getting. So error in only one. So it's p to the power 1. No error in two terms. That is 1 minus p square. And for here it is error in two terms times no error in one term. Okay. Now, in this case, what will be the correction mechanism? What will be the correction mechanism? Say, for example, for ancilla, what was my ancilla? 0, 1. I'm doing all these things. Therefore, the correction mechanism is that apply sigma x, which is a NOT gate, on the third qubit. Third qubit means the third qubit. Okay. So that means you will be getting sigma 0, 0, 1 plus beta, sorry, not sigma, alpha 0, 0, 1 plus beta 1, 1, 0 on sigma x third will give you alpha 0, 0, 0 plus beta 1, 1, 1 and alpha 1, 1, 0 plus 0, 0, 1 on sigma s third qubit will give you alpha 1, 1, 1 plus beta 0, 0, 0. Okay. Okay. Now again you see it, this is the desired state. So this is a correct state. But this is a undesired one or it is an incorrect one. So just for a quick note, for ancilla 0, 0, we got a alpha 0, 0, 0 plus beta 1, 1 as correct state. We have not applied any correction mechanism because in the very first state is my correct state. So why to like unnecessarily change it? And the second state was alpha 1, 1, 1 plus beta 0, 0, 0, which is one of the incorrect states. Now, similarly to alpha, like ancilla 0, 0, whenever you are applying it on ancilla 0, 1, initially you are getting something. I've calculated the probabilities over here. And then if I apply a correction mechanism, which is nothing but just apply a NOT gate on the third qubit in your superposed state. An application of that, we are again getting two different outputs based on two different inputs on ancilla 0, 1. And one of those outputs we are getting as corrected one, and one is an incorrect version. So again here, one is correct and one is incorrect. So let me write it down. So therefore, one output is correct and 1 is incorrect. So for P x for P x equals to 1. That is 1 bit error is okay. But 2 bit error, it is incorrect. Here it is 2 bit error. No? I should be having 0, 0, 0, but I'm having 1, 1, 0. So 2 bit error is something for which we are getting, say 2 bit error, we are getting an incorrect. And here for 1 bit error is correct. But we are able to correct. Also, there is a point that, but we are able to correct only one output, or say one of the two obtained states. Right? This is a correct one and this is an incorrect version. So we are able to correct only one state out of the two obtained states. Okay. Now, so also on another point is when I have ancilla 0, 0, I am not doing any correction mechanism, but automatically I am getting a correct state for when there is this correct state when I'm getting where there is no error. See, no error. This is my intended one and this is my actual one. So when there is no error, I don't need to do any error correction for ancilla 0, 0. When there is one error, I do not need to do any error correction on ancilla 0, 1. Now let us see what will happen for ancilla 1, 0 and 1, 1. So whenever your ancilla is 1, 0, what are the states that I'm receiving? I'm receiving two states. The first one is alpha 0, 1, 0 plus beta 1, 0, 1 and alpha 1, 0, 1 plus beta 0, 1, 0. From where you are getting these values, if you ask? We are getting these values from this table. Okay, for 1, 0, these are the two cases, 0, 1, 0 and 1, 0, 1. And also for 1, 0, it is 1, 0, 1 plus 0, 1, 0. So both the values we have just written it here, over here. Okay, now if ancilla is 1, 0, the logic is that Bob will apply correction mechanism is that Bob will apply what? Sigma x on second qubit, that is alpha 0, 1, 0 plus beta 1, 0, 1 on sigma x second will be what? We have to calculate an alpha 1, 0, 1 and beta 0, 1, 0 will happen. What? Let us compute that. So it will be alpha, second one is like flipped, so it's 0, 0, 0 plus beta 1, 1, 1 and this one will be alpha 1, 1, 1 plus beta 0, 0, 0. So again, this is a correct state and this is an incorrect state. And here again see, only when there exists one error in obtained output state, 3 qubit QVCC is able to correct it. Otherwise, if more than one error for ancilla 1, 0, it is incorrect. Okay. Now the fourth one is when ancilla is 1, 1. The fourth is, let me also write it down. So this is a third case, and 0, 1 is when it is the second case, and this is the first case. Yes. So when ancilla is 1, 1, it is alpha 1, 0, 0, just check it, plus beta 0, 1, 1, and alpha 0, 1, 1 plus beta, what it is? Like 100. Now, what is the correction mechanism? It's very easily understandable. So the correction mechanism is sigma x on first qubit. So we started with third qubit followed by second qubit. Now it should be third qubit because we have to correct and make this is alpha 000 and beta 111. So first qubit here is 1, so we have to make it a 0. And for beta, this qubit is 0. We have to make it a 1. So correction mechanism will be on this we have to apply this thing. On this we have to apply this thing. It will be alpha 000 plus beta 111, and this one will be alpha 111 plus beta 000. So if you notice here we are getting a correct output, and here we are getting an incorrected output or not correct output. Okay. So also now just to notice here that therefore out of all 8 cases that we have for each of the like ancilla combinations, only in 4 cases, only in 4 number of cases, the errors can be corrected. And where we are getting the incorrect set of errors. Okay. So the incorrect errors are when you are getting these particular thing. So first one is alpha 101 plus beta 010, or this is all these are the cases where out of all the 4 combinations of ancilla, like 1 is taken for each of them. Like for 00 this one, for 01 this one. Third one is for alpha 101 plus beta, sorry, just here, beta 010. And fourth one is where you are getting alpha 111 plus beta 000. So if you see it, here it is a 2-bit error. See, it should be 000. Here we are getting 101. So in first and third position, there is a bit flipping. Okay. So it's a 2-bit error. That is more than one number of error. Here also it's a 2-bit error. Okay. Because 1, second or third qubit has been flipped. Here also it's a like first and third qubit flipped. So 2-bit error. I guess I have written the same value. Just a minute. Alpha 1, 1 minute. So it's a 100 and 011. Yes, just a minute. Sorry. So this will be 100 and 01. So here also it's like a not this one. Sorry. So 011 and 100 I have written. But the incorrect values. Let me again just see alpha 111 and beta 000. 111 and beta 000 I have written. Then it is 110 and 001. So yes, yes. Thank you. So it's a so it's a 110 and 001. Yes. Here also it's an error and here also it's error. So it's not 2-bit, it's 3-bit. So it is also greater equals to 1, greater equals to 1, greater equals to. Okay. Now, probabilistic calculation of error, if we calculate that one, it will be, therefore, the total probability of error, will be, by calculating this, so it's a p x equals to 2, and in one case it is x equal to 3, right? So this will be, this is nothing but p cube, we all know this, and this is 3c2 into p square into 1 minus p times 1, so it is 3p square 1 minus p plus p cube, which is 3p square minus 3p cube plus p cube, which is 3p square minus 2p cube. This is the final value. Okay. Now, if say p is equals to 0.01, then 3p square minus 2p cube, this value will be somewhere, just put the values of 0.001, so it will be like 3 into 10 to the power minus 4, somewhere around this. Okay. Maybe with an approximation, but it will be exactly this. So maybe by ignoring or very small values, we can actually neglect that. I hope we are doing the same. So 2p cube is being neglected. So this is something that we can get. And for this much of an error probability, or say 1% error probability, okay, so I can get what kind of an improvement? So it's a great improvement. As we can see, initially it was like a 10 square. Now it is like 3 into 10 to the power minus 4. So if you divide it, you will be getting the error improvement of a factor by a factor of 3 into 10 square, so which is 300. Okay. So therefore, here the improvement is significant. Improvement is very significant. And the error or say quantum error is reduced from 10 to the power minus 2 to 3 into 10 to the power minus 4, that is by a factor of 300. So it is a great improvement. Okay. So this is the first error correcting code that we have seen. Now just a bit of more theory for that. Let me tell you, explain it. So we might cover another error correcting code, which we will start today, or some part of it we will see and try to analyze how it works. But before that, I just want to say that what type of error happens. So the 3-qubit error correcting code works on the principles of that if I want to send a particular quantum arbitrary state, say psi, which has a value alpha 000 plus beta 11, which we can establish very easily, like one psi to ancilla and only to C naught. By only introducing these basic quantum gates, we can devise this state alpha 000 plus beta 111, ignoring the amplitude, which is represented somewhere within alpha and betas only. But if we are able to do that, we'll be able to generate psi. And once we have psi, as Alice, I will try to send this particular quantum state to Bob. On that note, where I can get some error, maybe in the first qubit, maybe in the second qubit, maybe in the third qubit. Now, depending on whether it's a first qubit or a second qubit or a third qubit or first, second, then second, third, and first, third, or all the first, second, and third, or none of the first, second, and third. So based on this, we are getting all the 8 combinations which we are taking, and on thus we are generating a particular say possible set of quantum states that can be received by Bob. Some of them are erroneous, some of them are not erroneous. But now it is a Bob's responsibility or part of the responsibility of the error correcting code in order to detect the error, followed by correcting the error. Now for detecting the error, it is again using another quantum circuit where it is introducing 2 more ancillars, say 4th qubit and 5th qubit. So initially they contain all zeros, like both the qubits contain the value zeros. Now, based on what I have in my, like what I have received as Bob on my first, second, and third qubit, I will do some simple 4 CNOT operations on the ancillar qubits 4 and 5, okay, which is CNOT on Q1 and Q4, then Q2 and Q4, then Q1 and Q5, and Q3 and Q5. After all these 4 CNOT gates, we will be having certain kind of a similar pair we will be having in the phi 3L, which is the after ancillar, like that output that Bob is receiving after Bob has applied its own error correcting circuit. Got it? Now, whatever is the status of ancillar, see here in this circuit, whatever was the status of ancillar. Here is what I am referring. Here is what I am referring to. So this is the status of ancillar. ancilla after Bob has applied its own error correcting circuit, CCC or error correcting circuit. Whatever is the status, that will again feed to an error correction circuit, and based on that, it is able to see that for each of the correction mechanism or for each of the values of the obtained ancilla, there are four possible decision or say table or function table that were defined. Okay, what was the decision table? What was the decision table? That at phi 3L ancilla after phi 3L, let me write it this way, and this is the operation. It's what it should be doing. So if it is 0, 0, then operation is no operation. Don't do anything. If I have, say, ancilla is 0, 1, then it's a sigma x on third qubit. If it is 1, 0, then it is sigma x on second qubit. Let me tell. And if I have, say, 1, 1, operation that I should be doing is sigma x on the first qubit. This is just the beginning again for error correcting. This is the now. This is how the decision table or according to the function table, Bob will perform the like error correction mechanism and will ultimately check what is the output. But for each of the output again, there is a 50-50% probability that either Bob can, after correction mechanism, either Bob can get a correct output or an incorrect output. No, definitely not. But this is the error correcting code, which is a very simple one. And this is only when a one qubit quantum state, which is a single qubit one in a superposed state, 0, 0, 0, that or say kids of psi 0, psi is equals to alpha 0 plus beta 1, if that got like distorted. Now the thing is that, say, say for example, this is only when we are taking into consideration the bit getting flipped during communication. Now, what can happen is I might also face a situation where instead of the bit, I might also have a difference in phase. X is applied on which qubit, that depends on what is the ancilla that I am getting. So if it is only if you have these like psi 0 and psi 1, you of course cannot do it. So just like redundant bits, you have to here introduce some of the ancilla. Those ancillas will give you some intermediate status. Based on the status, you have to perform some operation. Based on those operations, now after that, you will be applying your sigma x on third or second or first qubit, so that you are able to tell that what in half of the cases you are getting correct and incorrect output. But again, this is the very fundamental one. And also, if you notice, it is able to correct only if there is an error. I've written the opposite. I don't think so. Just check it again. I guess for 0, 0, there was no operation. For 0, 1, we initially started with the third qubit, like modifying the third qubit. Let me check also. I guess so. So for 0, 1, yes. So for 0, 1, just say, see it over here. 0, 1, we are getting these things. For these are two things where we are getting 0, 1. 0, 1. So, but what was my desired state? 0, 0, 0 and 1, 1, 1. But I'm getting 0, 0, 1 and 1, 1, 0. So I should be doing 0, 0. I should just invert this third qubit and make it 0, 0, 0 and 1, 1, 1. Instead of 0, 0, 1 and 1, 0. That was the thing. But the thing is, what I was telling is, see, if you see here, whenever there was no error and whenever there was exactly one error, so all those places were correctly corrected, correctly corrected by Bob or by the 3-qubit error correcting code. But the cases where the chances of error is equal, and there is a possibility, because here also the chances of error is equal, but and there is a possibility of having error or flipping of bits for more positions, then only 0 or 1, that is neither in any positions or exactly in one position, is equal. That is equally probable if we have seen this thing. For 0, 1, we are getting values for two cases. First one was exactly one bit got flipped, and second one was bits got flipped. Similarly, for 0, 1, one case was where one bit was flipped, another case was two bits were flipped. Just see the correct steps. 2-bit error, 2-bit error, and 3-bit error. But for these like multiple bit errors, we are unable to process it with respect to a 3-qubit QV system. But their chances of occurrence is almost like equal. If now two things can be done. Either I should be able to correct these 2 qubits of errors as well, or I should make them so less probable that their appearance would not matter to me, because it is very negligible, so negligible that I can ignore it. That only maybe one position only error can happen for this particular setup. Say for example, for 3 qubits, only one position error can happen, not in multiple positions. Okay, so here is where some advanced error correcting things came into picture. Another thing was, what if instead of only the flipping of the bits, that is either from 0 to 1 and 1 to 0, if we have a certain more kind of error, so how to tackle that? So for that, another concept was introduced, which is called the phase flip error. So what I say, like errors can be of two types: the bit flip error, which we just have seen here in 3-qubit error correcting code, quantum error correcting code, where we have seen 0 is made 1 and 1 can be made 0. Another one is a phase flip error. Okay. Now bits are flipped because of certain kind of a disturbance. Phases also might be like changed because of some continuous evolution of quantum states. Maybe due to because of certain kind of a perturbation or say disturbance or noise or attenuation or decoherence. My phase also might got flipped suddenly, which is an error. Okay. So this can happen due to continuous evolution of quantum states. Okay. Say, so if psi is equals to, psi is initially, say for example, 0 plus 1 by 2, by 1 by root 2, so which means nothing but 1 by root 2 times 1 and 1. So due to some perturbation, say psi dash, it become now, which is k0 plus e to the power I5 k1 by root 2. Well, this is a phase factor, positive, negative, I don't know, but a phase factor that has been associated with my earlier state. So it was initially 1 by root 2 this thing. Right now it will become 1 by root 2 will be as it is. Now whenever it is k0 and k1, I was writing with 1 and 1. Whenever it is this thing, k0 plus e to the power I5 1. So I'll write it down 1 and e to the power I5. No issue with that. I can write it down. Now let me just take e to the power I5 by 2 as common. Then I will be getting e to the power minus I5 by 2 and column vector of this, just a minute, and this is e to the power plus I5 by 2. Now if we measure, so from the, I'm just taking this common, as common, which I can do that. Okay, root 2, just like that. So 2 was here, and I have introduced a root 2. Then accordingly, I have done certain modification. With say 2 is here to the power I5. So 2 to the power half, I have taken out, I have made it 2 to the power minus at the down value, or say the next to first column value is 2 to the power 2 to the power plus half. Likewise, I'm just trying to mold it. So now if we measure it, say if we measure the z component of spin y z component, that is the measurement axis and the phase also. In order to calculate, in order to correct the phase error, which should be encoded, your bits should be encoded in form of triplets in the diagonal basis. Diagonal basis means the plus minus basis. This is a plus minus basis. Okay. Therefore, your psi will be written as A plus 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 B minus minus minus. What is the meaning of plus? The meaning of plus is nothing but K0 plus K1 by root over of 2. So 0 on Hadamard gives you the plus. From that logic, I'm just writing it. Similarly, your minus is nothing but K0 minus K1 by root over of 2. So that is how, if I just write it down in this way, so it will be considering everything like root to all these things. So it will be A get plus 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 B get minus minus minus, where each plus and minus represents K0 plus K1 by root 2 and K0 minus K1 by root 2. Now, if I just write it down, the A plus 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 and B minus 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 again in computational basis. Right now, it was written in diagonal basis. So this is the output in diagonal basis. Now, if say psi is equals to A plus 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 B minus 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 is written in terms of our computational basis, that is with respect to 0 and 1, it will be get psi is equals to, considering I'm expanding it in this way. So it will be A plus B. After certain like calculation, you will see this thing A plus B by root 2 times get 0 0 0 plus 0 1 1 plus 1 0 1 plus 1 1 0. You can check it. It will happen the same. Plus A minus B by root over of 2 get 0 0 1 plus 0 1 0 plus 1 0 0 plus 1 1. So now we measure any of the qubits. Any one qubit we want to measure in the computational basis tense. Okay. So if we measure now, so now if we measure any of the qubits out of the 3 qubits, any of the qubits in a computational basis, states, then what will happen? What will happen? It will be in this way. So it is either A plus B by root 2 times. This is your K 0 0 0 plus this thing will happen. You can check it 0 1 1 plus A minus B by root over of 2 times 0 0 1 plus 0 1 0, or either we will be receiving it this, or A plus B by root 2 times 1 0 1 and this thing 1 1 0 plus A plus minus A minus B by root 2 into this thing, that is 1 1 or 1 0 0 plus 1 1 1, where we are just measuring the first qubit. So measuring the first qubit to be 0, we are getting the first one, or we are getting the second one. See, first qubit is 0, corresponding values we have, I am just written over here in this way. Similarly, from a minus b by root 2 also, first qubit 0 is this. First qubit 1 is the third and fourth one for a plus b by root 2 that I have written here. And the third and fourth one for a minus b by root 2 as well. That thing I have written over here. So these are exactly the same thing with respect to the first qubit. So with respect to the first qubit as 0. And this is with respect to the first qubit or say qubit as 1. Okay, now let us assume the Kate psi collapses to any one of the first states. After this, on assumption of that, we have got these things. And after this, say a parity checking is to be performed in the diagonal basis. So let's take, see, a parity checking. A parity checking is to be done in diagonal basis by introducing two ancillars as well as measuring ancillars after C0 operation. Okay. As per our last 3 qubit rule, whatever we have done almost the same thing. Error correcting rule. So once I have done that from the earlier equation, say from earlier expression, for our earlier expression, we can write that in diagonal basis, the collapsed state can be written as collapsed means after measurement. It can be written as A plus B minus plus A minus plus B plus minus. How the plus and minus have the respective meaning, where it plus and minus have respective meanings, whatever they have. Okay, I'm putting the values of zeros and one, all those things. So now the state obtained is either without error, or whatever we have got is the state obtained is either without an error or the state with only a single bit flip error, which can be corrected after some corrective action based on some, say, function table or decision table that was given to us following the ancilla measure. Okay. So now what we have done is we have just trying to see that what will happen if there is a phase flip error wise representation of the earlier ones. So how that can look like in the computational basis as well as in the diagonal basis. Now, in simple words, the next one is, so what we have seen again is a 3-bit error correcting code is able to handle only a bit flip error. You will be remembering this. So we definitely need some more powerful form of error correcting code. So here comes the introduction of Shor's 9-qubit quantum error correcting code, discovered by Peter Shaw, who also discovered the Shor's algorithm. Why 9-qubit? Because we here use 9 qubits for that, and error correcting code is obvious, you will understand. So why 9-qubit? Let us just do that. But it is able to handle both bit flip error and phase flip error. Let us see how. So bit flip is nothing but, say, a X and A and B are given, so which will make it a B and A. It is a bit flipping. And what is a phase flip? Phase flip means, say, Z is given, A and B, it will make it A minus B. Okay. For example, say, if you are given say Z on a 1 0, it will make what? What is Z? That is 1 0 0 and minus 1. And this is your 1 0. So it will make it 1 into 1 plus 0 into 0 and 0 into, so that is 1 and 0 into 1 plus another 0. So it is basically K0 itself. That is 1 0. So that means ZAB is equals to A minus B, where B is 0. So minus 0 is 0 only, right? But if it is 0 and 1, you will see that it is 1 0 0 minus 1 times 0 and 1. So ultimately it is a 0 and it is a minus 1. That is ZA comma B is equals to A and minus B. So here B has now become the minus. So 0 and minus 1 we have got it. Now whenever I call a mix of bit and phase flip error both, that can also happen in the network. So if this kind of an error like scenario happens, let us call Y AB. So first we will be doing, make it a B and A, or say make it a this phase flip. So phase flip will make it A minus B. Again that is on Z. Now again apply X. So it will be minus B A. So there means YAB will make it minus B A, which is the implication of both the bit flip error as well as the phase flip error. Now say how the short circuit look like. How this will look like is, so K psi is again the arbitrary state that you want to transfer. Again here will be two, okay, this will be A0 plus B1, arbitrary state with some amplitudes of A and B. There is a K0 which is an ancilla. There is another K0 which is another ancilla. All these things will be passed to a Hadamard gate. These two ancilla as well as the psi. And I'm applying C0 over here from psi to first one, as well as again from the psi to, that is the first qubit to third qubit. Okay, so this is your first qubit, this is your second qubit, and this one is your third qubit. And these are the three Hadamard gates that I'm applying. I will at least do the encoding of short today. Maybe the decoding we'll do tomorrow. Now, this is the phase flip coding, this part, first part. Till this part. What does this called? It is called the phase flip coding. Now, again, what? Again, we are introducing two ancilla for each of them. Doing like this. Now, this will make it this. And again from this, sorry, again from this, we are drawing this. Similarly, this one and this one. See how the 9 error qubits, or say 9 qubit error correcting codes coming into picture. Okay, so this was your initially 1, 2, 3. Now here after Hadamard, this is your first one, this is second, this is third. For this one, this is first, this is second, this is third. This is again first, this is second, this is third. So how many? 3 cross 3, that is 9 qubits are ultimately being affected. So it is a 9 qubit error correcting code. And this part is called the, I can do it with a different color. This part is a phase flip coding. Oh, sorry, bit flip coding. Just a minute. So that just a minute. Yes, so it is a bit flip coding, and this particular one is a phase flip coding. So this is the entire short 9-qubit error correcting circuit, which incorporates both the phase as well as the bit flip. Got it? Okay. Now let us do the encoding. Let us do the encoding. Say, let us see. We will do the encoding. We'll have an understanding. Say psi is equals to what? It is initially a kate 0 plus b kate 1. We'll start with the decoding, but today let us just target for the encoding part at least to be completed. And I guess it will be completed by whatever the time remaining. So psi is equals to a0 plus b1. So now what I'm doing, psi 0, 0. I'll put a paste. If you're having any difficulty, just let me know. Why? Because these things are very common now. It should be. So it's A000 plus B100. Now I'm applying 2 C0 operation. So C0, 1, 2, and C0, that 1 and 3. So this should make it A000 plus B, this thing, that is 110. And this will make it 000 plus B 111. Now Hadamard on all the qubits. Okay. On all the 3 qubits now Hadamard will be applied. So individually how it will look like, say just to tell you, Hadamard on 0 will make it kate 0 plus kate 1 by root 2. The second qubit of this thing will also be kate 0 plus kate 1 by root 2, kate 0 plus kate 1 by root 2. So if I just keep 1 by root 2 as common, then 3 times they are occurring. So 1 by 2, like root 2 whole cube. So it will make it 1 by 2 root 2. Agreed? So A divided by, it will be 2 root. I am just writing directly now. 2 root. And within the box, it will be what? It will be all the values, which is kate 0, 0. Sorry, kate 0 plus 1 times kate 0 plus 1 times kate 0 plus 1. Similarly, for this thing, it will also be like b by 2 root 2. And all the values will be within the bracket. It will be kate 0 minus kate 1 because I'm applying Hadamard on kate 1. So it will be kate 0 minus kate 1, kate 0 minus kate 1, kate 0 minus kate 1. Now, after a little like calculations, if I'm just doing, let me know. Those who are writing, you should be able to follow. So it will be just because I have already done it. So let me just write it. So kate 0 plus kate 1 times kate 0, 0 into this thing kate 0 plus kate 1 times kate 0, 0 into kate 0 plus kate 1 times 0, 0. From where I'm getting these 2 zeros? Because I have these 2 ancillars now. Okay, 2, 3. Again, like say 4. So 5, 6, and 8, 9. So considering the first sub circuit ka 2, 3, second sub circuit wala 2, 3, and third sub circuit ka 2 and 3. We are all taking those things. So it is initially 0, 0, 0, 0, and 0, 0. If I just take it, it will be like this times b by 2 root 2. The similar thing will happen. So kate 0 minus kate 1. This is 0, 0 Ket 0 minus Ket 1. This is 0, 0. And this is Ket 0 minus Ket 1. This is 0, 0. So this one will be a by 2 root 2. Just multiply it once, or do the not directly. If you do the not directly and multiply whatever you say, or just write the total together, it will be on application of, let me write, say C naught 1, 2. For each of them, I'm just writing C naught 1, 2, which is this thing, C naught 1, 2, and this is C naught 1, 3. So this is, I'm applying two operations together, 1, 3. So after both the operations, it will be something like Ket 0, 0, 0 plus 1, 1, 1 times Ket 0, 0, 0 plus 1, 1, 1, Ket 0, 0, 0 plus 1, 1, 1 plus B by 2 with 2, Ket 0, 0, 0 minus, it will be now 1, 0, 0, which is 1, 1, 0 first, then it will be 1, 1, 1. Okay, because of first 1, 0 will be 1, 1, then again this one and this 0 will be 1, 1. So it will be 1, 1, 1 directly. So 1, 1, 1 times this is Ket 0, 0, 0 minus 1, 1, 1, and this one is Ket 0, 0, 0 minus 1, 1, 1. Just expanding all the steps. Okay. Now for the simplicity or like alternate representation, let me just introduce 2 root 2 again. Let me enter it into all after all these terms and make it like 0, 0, 0 plus 1, 1, 1 by root. I can do that because root 2 cube is 2 root. So it will be ultimately a into 0, 0, 0 plus 1, 1, 1 by root over of 2 into or say anything, say product, tensor product, whatever you write, 0, 0, 0. I'm not writing this entire form by root 2, or let me just write it 0, 0, 0 plus 1, 1, 1 by root 2 plus b into 0, 0, 0 minus 1, 1, 1 by root over of 2 into 0, 0, 0 minus 1, 1, 1 by root 2 product nothing but. So this is 0, 0, 0 minus 1, 1, 1 by root over of 2. Okay. If you remember the relation between the computational basis and the diagonal basis, so these are nothing but class plus plus. Okay, which is coming from all of them. So it will be a. What will happen? You will be getting a plus 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 b minus minus minus. So this will yield a plus 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 b minus minus minus. Now I just need 2 more minutes. Just wait for 2 more minutes. Let me just complete it. Now let us assume that out of all the 9 qubits, just 2 more minutes, at most 1 qubit can be affected. Just a simple mathematics is remaining. So can be affected. At most 1 means if x represents a number, then it as at most 1 means less than equals to 1. Maximum 1 is possible. So the probability of this will be nothing but, we can write it down as x equals to 0 plus x equals to 1. Have how many total number of qubits? 9. So it is basically nothing but 9 is 0. Likewise, if I just write, it will be 1 minus p, because there is no error in any of the qubits, right? The number of bits where there is an error is equals to 0. That means no bit contains an error. There will be a no error has the probability 1 minus p. So it will be out of 9, it is 1 minus p to the power 9 plus 9c1 into p to the power 1 into 1 minus p to the power 9 minus 1, which is 8. So this is 1 minus p to the power 9 plus 9p into 1 minus p to the power 8. This is a binomial expansion. It will be something like, say, 1 minus 9p plus 9 into 9 minus 1 by 2 into p square. Likewise, we will proceed for this. Similarly, for this also, we will proceed like that, like 1 minus 8p plus say 8 into 8 minus 1 by 2, that is 8 into 7 by 2, that is 28, say 28 p square. And this one will be, I guess, 9 into 8 by 2, that is 36. So it is 1 minus 9p by plus 36p square. Let me ignore because these are very higher order terms. And p, if p is very small, so it will be very less. Plus 9p into this thing. So it is 9p minus 9 into 8, that is 72p square. Let us just ignore the PQ term. So ignoring P cube, P4, and all the higher order terms. Okay, now minus P plus P will be minus 9P and plus 9P will be cancelled out, so it will be nothing but 1 minus 36P square. That is, it is the probability that there will be error in at most 1 qubit. Okay, now, therefore, can we conversely say, therefore, the probability that we have error in more than 1 qubits, can I write it down as P of, say, x greater than 1, which is nothing but in terms of the theory of probability, x less than equals to 1, which means 1 minus 36p square, which is nothing but plus 36p square. Now, considering if p is very small, definitely we at least can say, sorry, not this 3, this is very, very less than p. Considering p is very small, so 36p square will be very, very less. Now, what is p? P is the error or probability that there will be error in exactly 1 qubit. But there is a error that there will be, p is the probability that there will be error in 1 qubit. 1 qubit. So, that means 36p square, that is very, very less than p means the probability that there will be error in more qubits, which is p into p, that corresponds to p square, will be very, very less. So considering p is very, very small, this clearly implies an improvement over the 3 qubit QVCC, quantum error correcting code, as the probability that there exists more than one error is very, very, very less. Whereas in case of a 3 qubit QVCC, it was almost 50% case. If you remember, say 50% error, we could correct it. 50% cases we couldn't correct it. But here, the error will happen in that probability, that like possibility itself is so less that definitely we can conclude that Shor's 9 qubit error correcting code is kind of an improvement over the earlier error correcting code, which was a 3 qubit error correcting code. Okay, and here is where we can end our discussion for that, for today's session. Okay, I'm just stopping sharing. Thanks for just giving me 4 more minutes. And thank you, Mamata. Thank you so much. So tomorrow we will start with the error decoding, followed by we will strictly enter into the teleportation, super dense coding, or teleportation and cryptography. All those things are revealed. Thank you.
Yeah. The slides will be shared. Don't worry. We have already sent all the slides. The material will be shared. Yeah. So those who have not taken the exam, please complete it. Yeah. So I think, thank you, Nivedita ma'am.